Welcome. We will start one new topic, that is randomized complete block design. So, we will be spending around 2.5 hours on this topic, and in this lecture we spend around 30 to 40 minutes of time to introduce randomized complete block design, abbreviated as RCBD, and the content of this lecture presentation are: we will first tell you when blocking is needed, that is under introduction. Then what is the pictorial representation of RCBD, how RCBD can be represented in terms of tables, some layout, and then one part of statistical analysis, that means how do we partition the data as well as the total variability into different component, like the way we have done in one way analysis of variance, ANOVA. So, first understand important thing, that the process model what we have discussed in earlier, we will repeat this. It take inputs and convert to value added outputs. Suppose the output characteristic is y, this y also governed by set of controllable factors x and set of uncontrollable factors z, and this conversion process makes inputs to value added output. Now, these uncontrollable factors and sometimes we can control, but we will not control because of cost and other things. But whatever may be the whether controllable or uncontrollable in this situation, sometimes they actually are treated as noise. So, this is basically nuisance factor, nuisance factor. Now, this nuisance factor cannot be ignored all the times. Sometimes because of randomization their effect can be nullified, but many a times what happen, their effect are there, and if you do not do careful design for the experiment, and accordingly if you do not do experiment, those noise or nuisance factors effect will be there, and you will estimate the effect of the treatment with reference to controllable factors will be biased, or other sense will be incorrect. So, as a result, it is essential in many situations to block the effect of nuisance factor and then conduct experiment by blocking the nuisance factor, and then get the data and analyze the data with incorporating the nuisance factor into consideration, so that the treatment effects can be estimated while controlling the nuisance factors. So, the important concept for under such case is known as blocking. By blocking we mean that we will block the effect of nuisance factor during experimentation. We will do experiment in such a manner that the effect can be isolated. Okay. So, now see, the nuisance factor can be unknown and uncontrollable. So, you cannot do anything because you do not know what are those factors. So, only randomization and sometimes that having more number of data that can that can help you in eliminating that effect. But many a time nuisance factors are known, sometimes they are uncontrollable. So, when nuisance factor known and uncontrollable, the analysis technique known as analysis of covariance will help you in controlling the effect of uncontrollable nuisance factor and then estimating the effect of the controllable factors. But when sometimes it is known as well as controllable, then it is better to block them, means control by blocking. So, today's introductory lecture will be on randomized complete block design. So, I mean you know the blocks, you know the controllable factors, and you will block the nuisance factor in such a manner and also conduct the experiment in such a manner that under every block you will be able to do experiment considering all the levels of the controllable factors, and you will be having sufficient number of experimental runs through proper randomization, so that both the randomization, blocking and replication, these three principles will be adopted adequately, and the data what you gather, it will represent the actual condition under which the experiment should be done. Okay. I will give you one example here. Before giving you the example, I want to tell you that this lecture also prepared based on the materials taken from the book written by Montgomery, Design and Analysis of Experiments. So, here the experiment is that suppose you want to measure the hardness of some metal sheet, let it be, and what happened. So, you will have from this metal you can prepare test coupon, every coupon is basically from a piece of this metal sheet. Let there are 4 diamond tips, So, these diamond tips, basically this will be used to, this is, you know that the hardness measurement. So, the diamond tips, the penetration of the tip on the metal coupon, if it is fall from certain height, maybe the penetration will give you a measure of the hardness. Okay. So, this is the situation. Now, it may so happen that, so you use different test coupons, and suppose 5 test coupon for tip 1 or 4 test coupon for tip 1, another 4 test coupon for tip 2 and tip 3, tip 4, like this. And then if you analyze the data, you get some results, but that may be erroneous, because the test coupons which may be prepared of the metal sheet of different quality in terms of hardness. So, under such situation, what will happen, maybe the data will show you that the test coupon differs, but that difference may be due to the material effect or the test coupon effect rather than the tips effect. So, under this situation, what you do, you block the test coupons. You create test coupon maybe from homogeneous set of the sheet metal, and then suppose 4 test coupon you prepare, and from a homogeneous set, that is a block 1, from second homogeneous set another 4 test coupon, third homogeneous set another test coupon, and then in each homogeneous set use all the tips and assign the tips randomly definitely. So, then what will happen? You will have a pictorial representation of blocking like this. You see this block 1 with reference to the that metal the whose hardness to be tested is homogeneous. Block 2 is another homogeneous set. There may be variability or the difference in hardness between block 1 and block 2, but that is not of importance. Our important thing is that we want to know whether all the tips are giving you similar measurement or not. So, treatment here is the tips, but if you ignore the coupon effects, material effect, you will get erroneous results. So, during design, that is why you are creating homogeneous sets of blocks, and each set of blocks will be used for all the treatments or will be attributed to or will be administered to all the treatments. Here all the tips will be used. So, material the representation is like this. Block 1, see all the 4 tips were used, block 2 4 tips were used, block 3 4 tips were used, block 4 4 tips were used. So, this is what is known as that randomized complete block design. The word complete indicates that each block contains all the treatments. You see, in every block, here block with respect to test coupon, in every block all the 4 tips were used. By using this design, the blocks or coupons form a more homogeneous experimental unit on which to compare the tips. Effectively, the design strategy improves the accuracy of comparison among the tips by eliminating the variability among the coupons. Within a block, the order in which the 4 tips are tested is randomly determined. That means, blocking within block randomization, and also sometimes what happen, you may go for replications also, more than one runs, experimental runs. Okay. So, under this, as we are not interested in knowing that how the materials are affecting, rather we are interested in knowing that whether tips are affecting in the measurement. So, maybe under each block one replicate is sufficient for per treatment, because effectively the number of blocks will be used as some kind of replication for each of the treatment levels. Okay. Then what will be the data? Data will be like this. In general, your treatment will be having a number of labels. Suppose there are b number of blocks, and suppose for each block treatment combination you are doing one experimental, you are conducting one experiment only. Then you will be getting data y11 to y1b, something like this, and this side, this is that y1 dot is the total row total, y2 dot is the second row total, like this ya dot is the 8th row total, and in the other in the similarly in the column also column totals, corresponding column totals, y dot 1 first column total, y dot 2 second column total, y dot b third column bth column total, and y double dot, this is basically the grand total. So, fine, but essentially what you are getting? You are getting data y11 to this a treatment 1 to a, blocks 1 to b, this data set you are getting. So, then what is the model here? Your any observation, general observation which can be written at yij. So, any general observation yij, this can be written in partition or written like this, it has the grand mean effect plus tau I, that is the treatment effect, plus beta j, this is the block effect, plus epsilon I j. This is what is the random effect, random error. So, with reference to the example, that means treatment, it is the tips, whether the tips give effect is there in the measurement, blocks are nothing but the test coupon and random. So, a general observation having grand average or grand mean component, treatment effect, block effect and random component. This is what is the ANOVA model or general, or what I can say that fixed effect model, fixed effect data effect model. Why? We are considering the treatment as fixed. Any observation will be, and this mu, tau I, beta j, these are all the parameters of this model. Here I stand from 1 to A and j stands from 1 to B. Okay. So, our hypothesis of interest is here H0, that mu 1 equal to mu 2 dot 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 equal to mu A. So, that means there is no the treatment effect, that means no difference amongst the means, the means of the treatment levels. And what is our alternate hypothesis? Mu I not equal to suppose mu j for at least one pair. So, this is known as hypothesis for means. Suppose if you want to use the hypothesis for the treatment effects, then you write correspondingly tau 1 equal to tau 2 dot 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 equal to tau A equal to 0, and alternate one is tau I not equal to 0 for at least 1 I. But please remember, we are not making any hypothesis regarding block, no hypothesis. Why? Because block is a uncontrolled, block is here the test coupons are known and there is variability, there is variability, and we are not interested to know how the different test coupons having different kinds of variability. Rather, we are interested in the treatment effect, that is the tips effect. So, for block or here in with this example the test coupon effect, we are not making any hypothesis, we are not interested to do this. So, under such situation the calculations will be like this. What is in general y I dot means, that is the row total, ith row total, then y dot j is jth column total, and that you know. So, when you are considering row total, that means you are going across all columns. So, j equal to 1 to b, that y I j, and I equal to 1 to a. So, when you are going for across for a column, you are going across I equal to 1 to a, y I j, I j equal to 1 to b. Then if I want the average y 1 dot average, so it will be 1 by b y 1 dot. If I want y dot j average, this will be 1 by A y dot j. Okay. Suppose I want the total average, total observation total, grand total, then I equal to 1 to A, j equal to 1 to B, y I j. And if you want grand total, this will be 1 by A B, y dot dot. So, these are the way from the calculation part, and ultimately what is the total number of observation in equal to total number of observation equal to A into B. Okay. Let us see that the individual, when you collect data, you have y I j equal to y double dot bar, which is grand average, plus y I dot bar, suppose minus grand average, plus y j dot bar minus grand average, plus if I write y I j, then if in order to make left hand and right hand equal, see this and this will be cancelled out. So, that means minus y I dot bar minus y j dot bar plus y double dot bar. So, we have now if we do little modification y I j minus y dot dot bar, then it will be y I dot bar minus y dot dot bar plus y dot j bar minus y dot dot bar plus y I j minus y I dot bar minus y j dot bar plus y dot dot bar. So, you take some square it, take j equal to 1 to b, take j equal to 1 to b, take summation I equal to 1 to a, summation I equal to 1 to a, and do algebraic manipulation, and finally what happened, you see the slides, you will see that this ultimately become first quantity b of this, second quantity a of this, third quantity this, and there are some covariance type of things, the 2 times of this. And if you take the sum, you will find out that the 2 times this covariance kind of thing, that will become 0, and as a result the resultant will be, this is the sum total, sum square total y I j dot minus this square equal to this plus this square plus this. So, sum square total is now divided into sum square treatment, sum square blocks, and sum square error. That is what you have seen, because your original data individual y I j you have written mu plus tau I plus beta j plus epsilon I j. So, if I write this minus this equal to this, then ultimately the total derivation is coming from the treatment point of view, block point of view, error point of view. As a result, SST equal to SS treatment plus SS block plus SS error, and you will find out the degree of freedom will be AB minus 1, because your n equal to AB, and here A minus 1 treatment plus B minus 1, and then rest will be AB minus 1 minus A minus 1 minus B minus 1, sum will be like this. Okay. So, what happened, you will find out that your error will be A minus 1 into B minus 1. So, degrees of freedom for total is this, treatment this, block this, and this will become A minus 1 equal to A minus 1 into B minus 1. Fine. Now, you require to compute SS treatment, SS block, SSE, and that already you have seen. This is SS treatment, this is SS block, this SS total, SS treatment, SS block, SS error. This can be written in this format, that is EGOA. So, this can be computed using SST equal to this, SS treatment this, and so Here you require average, here you do not require average, only that from the total square point of view you are getting this. This kind of computation you have seen in one way ANOVA also. Okay. And then what you require? You require to prepare the ANOVA table. Please keep in mind, in ANOVA table, first thing you have to do is sources of variation. In RCBD with one factor, sources of variation, first one is A, that is the factor. Then block. So, if I say this is block, this is what is your treatment. Then error, then total. You require to compute SS, so it will be SSA or SS treatment, SS block, SS error, SS total. You require DOF, A minus 1, B minus 1, A minus 1 into B minus 1, A B minus 1. Find out MS, SS, that is MS treatment equal to SS treatment by A minus 1, similarly MS block, similarly MS error. Then find out F, we are interested only in this first one. So, F0 is MS treatment by MS error, which follows F distribution with A minus 1 degree of numerator and A minus 1 B minus 1 denominator degree of freedom. See the difference between this and one factor complete randomized design. You will find out the one of the difference is that here A minus 1 is there, earlier denominator degree of freedom is changed, there A into n minus 1 and here A minus 1 B minus 1, and essentially the major difference is that without blocking, if you do this component you avoid, eliminate, you will not consider, but when you are actually blocking it, you are partitioning the sources of variation into blocks also. So, this will be taken out, and as a result what happened, the F0 and other statistics value will become different, and you will be getting the correct kind of result. And then you will reject H0 if F0 this is greater than a threshold value of A minus 1, B minus 1, threshold value of alpha, level of significance. So, this is what is for today. So, I told you that what is RCBD. So, RCBD is randomized complete block design. Randomized word is there, every experiment, the order and the way material and the operator, other things are assigned, they must be random. Here block is coming because you know there are certain nuisance factors, and those nuisance factors are known and controllable. So, you can block them during experiment. We have given one example where tips versus the test coupon is block and different tips are treatments. And then what we have discussed, that we know that there are different sources of variations. With the example given, with one factor, the factor or treatment is one variation, one block another variation, there will be random error, that is another variation. So, you know the sources of variation, and accordingly you are calculating SS, MS, different degrees of freedom and F statistics. Here you are not interested to know whether the different blocks are different or not. So, that is why you are not conducting any hypothesis testing related to blocks, but you can do that also, but it is not required here. So, we will in the next class we will see one example on blocking, and then there are many more critical issues in blocking, those will be discussed. So, thank you very much.